Hello, everyone, and welcome to this episode. If you're taking AP Chem, and I do hope you are, at some point in your chemistry travels, you're going to run into Unit 6. And Unit 6 is all about thermodynamics. So here's our list of topics for Unit 6, and if all goes according to plan, in a short time, we'll make it through all of those, and you'll have a better understanding of Unit 6 thermodynamics. So let's get into it. We're going to start out talking about endothermic and exothermic processes here in 6.1. And it's helpful to know the definitions of those. And as we do the definitions, we're going to use the terms systems and surroundings. System is the thing that we're studying. Maybe it's in our calorimeter cup, maybe it's in our reaction, but the thing that we're interested in is the system. The surroundings is everything else in the universe. And there's often heat transfer between the system and the surroundings, or vice versa. And in an endothermic process, energy is transferred from the surroundings into the system. And we've got some examples here. So, for example, if I'm boiling water in a pot on my stove, I'm putting in heat, and that water is absorbing the heat and vaporizing. So, the system, the water is absorbing heat. Anytime I'm cooking, baking bread, frying eggs, or anything like that, you have to add heat to it. And so that heat causes the change to happen. Your food is absorbing that heat, and that is endothermic as well, if we consider that to be the system. Plants absorb energy from the sun. So if we think of our plant as the system, it has to absorb energy from the sun in order to take the carbon dioxide and water and turn it into sugars and oxygen. So again, energy has to go in. On the other hand, in an exothermic process, energy is transferred from the system out into the surroundings. There are lots and lots of examples of exothermic reactions. Think fire, anytime you have fire going on, like burning of wood around your campfire is exothermic because we see the heat. We feel the heat, we see the light coming out of it, and heat is coming out to the surroundings. So share that at your next bonfire. I also included this one in here, which is kind of, in a way, counterintuitive and kind of messes with people's minds a little bit. But when something like water turns into ice, and it freezes, a lot of people think that's endothermic because it's getting colder and it has to get, but it actually has to lose its heat in order to freeze. And so from the perspective of the ice, it's exothermic. The water is giving away its heat and turning into a solid at the same time. So just to kind of give you a little tip, I made a quick list of endothermic and exothermic processes. So the endothermic ones are going to be things like melting, boiling, and sublimating or subliming. Those actually require, for something to melt, it actually has to absorb heat to move to the higher state. And so those are endothermic, and reactions that absorb heat, they feel cool to the touch, like in a cold pack or something. Exothermic reaction things include freezing, condensing, depositing. That's when something goes from the gas directly to the solid state, or reactions that give off heat. And I just wanted to point out, I do have a whole playlist of videos with more detail on a lot of these things, like the energy of phase changes or reactions that give off or absorb heat. So you can check those out as you want. Once we know whether things are endothermic or exothermic, it's time to communicate that information. And sometimes we use enthalpy diagrams in order to convey whether something's giving off or absorbing heat. And enthalpy diagrams show the relative amount of enthalpy from before to after during a process. And they're not meant to be super accurate or even to scale. They're kind of just a visual aid to help us imagine what's going on. So, for example, in an exothermic process, the system loses energy to the surroundings. So the enthalpy, or the energy of the system, is going downhill. So we'll see like an upper level for the reactants, a lower level for the products, and an arrow showing, yeah, we're going downhill because we're giving off a bunch of energy. On an endothermic reaction would go uphill. Now, they come in many forms. There's no one correct way or one correct format for an enthalpy diagram. So I'm going to show you several. And here's a couple of showing chemical reactions. One that is endothermic, or exothermic, sorry. And it's negative 890 kilojoules, turning methane into carbon dioxide and water. So that's going downhill. Energy would be coming out. On the other hand, taking hydrogen and iodine and making the friendliest compound in the whole world um, actually involves absorbing some energy, 26.5 kilojoules. So notice this is 890, that's 26.5. They're almost the same size. Again, it's not meant to be to scale. And note also there's no numbers on the left-hand part of the graph because this is relative. Actual amount of enthalpy in a substance is actually really difficult to determine. There's lots of molecules in there. You have to add them all up, and it's really difficult. But it's very easy to find the change in enthalpy or the change in energy when a process occurs. And enthalpy diagrams or energy diagrams can be used not only for chemical reactions, but for physical processes as well. So here's again something that's exothermic, giving off some heat coming out, but the change from water solid to water liquid is endothermic. So that's not a chemical change, but that is a phase change, and there's an energy change associated with it. So we can use an energy diagram to show that. And now let's talk about heat transfer and thermal equilibrium before we get into some problem solving. Heat transfer is really important, and it involves sort of molecules becoming in contact with each other. So, for example, if you put a hot object with a cold object, there's only one direction that the heat is going to go, and that's going to go from the hot object into the cold object. So, little joules of energy, little kilojoules of energy, calories, if you're from America, you might do that. And it happens because the higher temperature molecules have higher kinetic energy, and they're colliding with a whole bunch of things with each other. And if you put them in contact, they start colliding with the other molecules. And just like pool balls on a pool table, one ball hits another ball and transfers its energy to that ball or molecule in this case. These start moving faster while these lose their energy. And eventually, they get to a situation where they are at thermal equilibrium. They all have the same average kinetic energy because the energy has been now evenly distributed throughout all of the molecules that are present. So that happens a lot. I'm going to show you a couple of different representations of that. Here's a word representation if you want to pause and write this down. When two substances of different temperatures or phases interact, one substance initially has a higher kinetic energy and the other has a lower kinetic energy. The higher energy molecules collide with the lower energy molecules, transferring their energy to them. The lower energy molecules gain energy until the entire sample has the same average kinetic energy. This state is called thermal equilibrium. And I included phases in here for an easy example, like if you put ice in some warm water, the ice is cold, the warm water is warm, but the ice will gain the kinetic energy from the warm water. The water will cool down a little bit, and ultimately the ice is probably going to melt, and they'll all end up at the same average kinetic energy. All right, and so it's average kinetic energy. Not all the molecules have the same kinetic energy, but they will have the same average overall. Here is a picture of some hot water going into some cold water, and your final temperature, once the hot and the cold meet, the final temperature is going to be somewhere between the cold and the hot. They'll meet somewhere in the middle. It might not be exactly in the middle, depending on what temperatures and how much of each there are, but they'll meet somewhere in that middle. I wanted to show you this because I'm seeing some questions from the College Board regarding thermal equilibrium and using these Boltzmann distributions of molecules. And this kind of distribution, I did a whole video on those, involves showing average kinetic energy. So at any given temperature, let's do this low temperature, some molecules have really, really low kinetic energy. Some molecules have really, really high kinetic energy, but the majority of them are kind of right there. If the temperature goes up, the whole mountain goes to the right a little bit. You'll still have some molecules with low kinetic energy and more molecules with high kinetic energy, but on average, the average has shifted a little bit because you're at a higher temperature. Now, I just wanted to sketch on here what would happen if I took a cold object with this distribution and combined it with a warm object with this distribution. What would the resulting distribution look like? Now, because if you think about temperature, they will meet in somewhere in the middle of the two temperatures that you're joining. The Boltzmann distribution would be somewhere in the middle between these two. That's a terrible drawing, but hopefully you get the idea. It will be further to the left, and of this one, farther to the right, somewhere in the middle, and about somewhere in the middle in terms of their peak heights, because the area under the curves has to stay the same. Now, if I'm mixing two substances, this would be a bigger curve, but the idea is hopefully there. You might see this represented as a Boltzmann distribution type of question. And now let's get into talking about something called heat capacity or specific heat capacity. And this involves adding energy or taking energy away from something and having it do a temperature change, not a chemical change or anything like that. I like to split this unit up into two halves: energy and physical changes, in which nothing new is created, and energy and chemical changes, in which something new is created. Here we're talking about heat capacity, which is the energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. It's given in joules per gram degree or calories per gram degree if you're in America or just old like I am. You might have seen this one before. But today we're generally using joules per gram per degree. So you got to imagine a whole bunch of substances, and you have 1 gram of each one of those substances, and you got them all lined up. And you want to go ahead and raise all of their temperatures, all your 1 gram samples, by 1 degree Celsius. Turns out they don't require the same amount of heat to do it. And you might have a chart in your folder, something like this, where there's a list of substances and their heat capacities, which are given in joules per gram degree. And you can see from this chart, there doesn't seem to be any logical pattern. But what these numbers mean is that, like, for example, aluminum, it requires 0.897 joules to raise every gram of it every degree. So that's its constant value. Okay, and other substances from the periodic table have their own constant values. What I find interesting is that there's actually a pattern. Not totally obvious on that first chart, but there is a pattern. Check this out. This is a screenshot of a periodic table showing color-coded heat capacities. Check it out. If you look at this, it's definitely a pattern because all the red ones are way up here at the top. Then you kind of phase down into the blues and the dark blues and the purples, which are the lowest heat capacities. So it turns out the heavier elements at the bottom of the periodic table have the lowest heat capacities. The lighter elements at the top have higher heat capacities. And I always wondered about this because here's another graph. This is heat capacity versus atomic number. I like to show this in my class as well. But it's a pretty bit steep drop off from hydrogen to helium, and this is all their atomic numbers, again, way up here into the higher, heavier elements. And it bothered me for a really long time because I was like, wait, shouldn't heavier elements like lead and gold need more energy in order to like crank up their temperature a little bit? You know, they're heavier. There's more stuff in them: protons, neutrons, electrons. And that's true until I finally learned that it's actually a lower heat capacity because to add up to a gram, there's fewer atoms needed to add up to a gram. And so you're actually heating up fewer atoms along the way. And so it requires a small number of joules. And heat capacity is, again, the energy needed to just change the temperature, and temperature is average kinetic energy. So to make molecules go faster, you just need to add energy, and some things have more energy and some have less. Now, you're probably going to have to calculate the total heat during a temperature change. I'm making this video in 2025. The 2024 exam had a lot of heat capacity on it. I'm going to say it's 100% likely it's going to show up again, maybe not to the extent it did last year. But you'll be given this formula and you have to know how to use it. So, for example, how much heat is absorbed by an 80-gram sample of iron as it goes from 20 to 100 degrees Celsius? The formula goes like this: Q, which is the letter we use for heat, because, of course, it's obvious, right? Q for heat. The quantity of heat is equal to the heat capacity of the substance times the mass of the substance times the change in temperature of the substance. Okay. And a quick note about the change in temperature: by convention, we always do T final minus T initial so that we get the appropriate sign of our answer at the end. So here it is. 0.449 is the heat capacity for iron, joules per gram degree. 80 grams, that's for every gram. We have 80 grams, so we're multiplying. And it goes from 20 up to 100. So 100 minus 20 gives you 80. And that gives me 2,873 joules that iron would absorb. Another quick example. Using that same formula, example 2, if you add 2,000 joules, now that's the actual amount of heat. are added to a 100-gram sample of gold at 25, what's its final temperature? And this is just another example. If you know any 4 of the 5 things, you can solve for the fifth one. We're going to plug 2,000 in for the joules, the heat capacity of gold, which is very low because it's a heavy element, 100 grams, T final minus 25, and if I do my algebra correctly, I can predict that gold will increase to 180 degrees Celsius with the addition of that heat. Okay, and now some of you, a lot of you probably know this, but some of you might be wondering, well, how do they figure out what these heat capacities are? Like, how does anybody know how many joules it takes to change their temperature? So what we do is we actually compare it to something that we do know, and usually that's water. Water is known to have a heat capacity of 4.184 joules per gram degree. In fact, we know that because it's kind of how they defined heat. Okay, way back in the day, a calorie was defined as the amount of heat it took to raise 1 gram of water 1 degree Celsius. A calorie is the same as 4.184 joules, so we've basically defined the heat capacity of water to be 4.184 joules. So if we compare something else to it, we can then get a judgment about its heat capacity. So usually what we do is we take some hot metal and we heat it up to some temperature that we know. Usually it's in boiling water, somewhere around 100. And we have some cool water in a calorimeter, an insulated cup usually. And then we get them together and we get them to go to thermal equilibrium. So they end up at the same final temperature. The water is warmed, the metal cools, same final temperature, and then we can do a calculation as to what its heat capacity is. And I want to show you one of those calculations because now, and even though it's not as likely that you're going to have to do this calculation on the exam, it's more likely the first one, but it's good to know what this is all about because you're probably going to have to do the labs and things like that. So we're basically going to say, okay, when thermal equilibrium is reached, the Q, the heat lost by one thing, is equal to the heat gained by the other thing. We're assuming no heat loss to the surroundings, which is a terrible assumption in a lot of situations, but we're going to assume that. So Q lost, Cm delta T for that one, plus Cm delta T for the other one is going to add up to 0. 0 energy lost to the surroundings. So let's take a look at an example. I already worked it out to save time. Let's say I have a piece of molybdenum, just because why not? And it's initially at 100 degrees Celsius, is dropped into 244 grams of water at 10 degrees. When the system comes to equilibrium, the temperature is 15.3. So the water went up a little bit. Didn't go up a lot because water has a really high heat capacity compared to metals. Metals will change their temperature a lot more. I'll pause here and say one thing that in conceptual form that I tell my students all the time. The higher the heat capacity of a substance, the lower and slower its temperature change is going to be. It's not going to change much. The lower the heat capacity of a substance, the higher and faster its temperature change is going to be. So the molybdenum is going to change a lot. The water is going to change very little. So what I do is Cm delta T for one, and I'm just going to assign the molybdenum to one side. Cm delta T for the other side, which is the water, and we're going to add it up to 0. So watch what happens to the negative signs. C, we're solving for C. I don't really know this yet, so I'm just going to leave it blank, but I do know the mass of molybdenum and the temperature change, which was final minus initial. That's going to give me a negative number, but that's okay because it's dropping in temperature. It's going in the negative direction. Minus heat capacity of water, mass of the water, and the temperature change of the water, which is positive in this case because it's going up, 15 minus 10. Set it equal to 0 because no heat loss. And then I do some math. C times negative 20,000 minus 5410 equals 0. Throw that over to the other side, divide by 20,000, and I got 0.269 joules per gram degree for the molybdenum. And that's the unit for heat capacity. So make sure you know the units for that. Included under the category of energy and physical changes is energy and phase changes. So a couple of quick terms that you'll need to know. One is the heat of fusion. The heat of fusion is the amount of energy required to melt 1 gram of a substance at its melting point. And the heat of vaporization is the amount of energy required to vaporize a substance at its boiling point. Both are given in joules per gram or sometimes kilojoules per mole, in which case it's called the molar heat of fusion or the molar heat of vaporization. And why do we need to know these terms, or what's the deal with them? Well, it turns out you're likely to see a chart like this if you haven't already in your chemistry travels. And it's what's called a heating curve, which is kind of a misnomer, and it kind of bothers me a little bit because it's not really a curve. It's actually a bunch of line segments here. But what it's trying to show is the addition of heat and what happens to the substance when heat is absorbed by that substance over a certain length of time. So, for example, if I had some ice at minus 50 and I started adding heat to it, it wouldn't melt until I get it up to zero, which is its melting point under normal conditions. But then if I were to watch the temperature while this thing was melting, what I would notice is that the temperature doesn't change at all. There's no temperature change during the phase change, even though heat is being added. And that is because extra heat is needed to break the bonds or the attractions between the molecules. If they're stuck in the solid state, they are locked in place and you need to break them free. And that takes extra energy. And that's the heat of fusion. And then you can heat it up again to its boiling point, which in water's case is 100. And then extra energy is needed to break the water molecules free from each other. You might have noticed if you're boiling your pasta water at home, you get it up to 100 and the pasta just cooks. It doesn't just keep going indefinitely. You're turning it into steam using that heat of vaporization. And so, big thing is that you can never have a temperature change or a phase change at the same time. You can do one or the other. Just for your common knowledge, the heat of fusion for water is 334 joules per gram. Sometimes you'll see it reported as 333. I was told 334 growing up, so there you go. Heat of vaporization is 2260 joules per gram for water. Now, these are probably not something you have to memorize, although it's nice to know and just have in your head. These would likely be given to you on any type of question that you might encounter. So, important concept to remember when it comes to phase changes. When adding or subtracting heat from a sample, there can either be a temperature change or a phase change, but not both at the same time. When you get to the temperature of a phase change, extra energy is needed to change the phase, which is independent of the energy for the temperature change. And it's also, going back to my chart, it works the other way around. So if you cool something down to its boiling point, you would see not a temperature change going on, because at that point, the molecules are coming together and forming new attractions. If they were in the gas phase and now they're coming to the liquid phase, those attractions release energy in the same way as a chemical bond releases energy, and so we don't get any temperature change out of it. A couple of quick examples, just so you can see some. You may have to do this, you may not. For example, how much heat is needed to melt 50 grams of ice? So if I got a chunk of ice sitting here and it's at its freezing point, melting point, how much energy does it take to do it? Well, the formula we need is kind of like Q equals Cm delta T, except there's no delta T because there's not a temperature change. Q equals the heat of fusion times the amount. Maybe if the amount is in moles, you'll need kilojoules per mole times moles. Or if it's in joules per gram, multiply by grams. In this case, 334 joules per gram times 50 grams is a little over 16,700 joules, which I rounded to 3 sig digs right there. Another quick question: how many grams of water can be boiled away by adding 130,000 joules of energy? Well, in this case, I know how much heat it is. I know that the water will take 2,260 joules to vaporize 1 gram of it. And if I solve for the grams, I get just over 57 grams that can be vaporized by the addition of that much heat. All right, let's do another one. This one, how much heat is needed to heat 50 grams of water from 22 to 100 and then vaporize it? So imagine you got a beaker, it's on a hot plate, 500 grams of water, you heat it up to boiling and then walk away and you come back later and it's gone. How much heat did it absorb? Well, in this case, there's actually two different things going on. One is a temperature change and the other is a phase change. And when this happens, and it may happen that you'll see these in types of problems, is that you have to treat it separately. Let me show you the solution for this one, again, to save time. What we can do is say, all right, I want to know the total heat. But there's two processes, Q for the heating and Q for the vaporization. And Cm delta T for the heating, heat of vaporization times mass for the vaporization part. And if I treat them separately and just calculate each one separately and add up the total, that's what I'm going to do. So 4.184 times 500 times the 78 degrees it's going up. Add to it the 2260 times the 500, and you get two different numbers. This one is vastly bigger than this one. It takes a lot more heat to vaporize than it is to change the temperature. but it works out to just under 1,300,000 joules or 1293 kilojoules. Here we have the heating curve for another substance, in this case iron, as opposed to water. And I want you to notice how similar this graph is to the one we saw for water. It actually has 5 linear segments on it, and again, so it's not really a curve, it's more of a set of segments. But there's some differences as well. One is that the first flat part of the graph happens at around 1500 degrees Celsius. So that first flat part is going to indicate the melting temperature of iron. So whatever the temperature that's at, that's the melting temperature. And then we would continue on up in the liquid phase until we get to the boiling point of iron, which is somewhere just south of 3000 degrees Celsius. And you can look up those actual values somewhere else. We're just estimating based on a graph like this. So every substance, in theory, has a graph something like this that would show solid, liquid, and gas, and then their 2 phase changes and their temperatures. Now, some of you are very bright and curious, and you're probably wondering, why is this line steeper than that line? And why is this line even a little bit flatter than these other 2 segments? And that's because in the different states, we're undergoing a temperature change here. Those different states may have different heat capacities. And so the steeper the line, the faster the temperature change is happening, which means that it's got a lower heat capacity. Metals tend to have fairly low heat capacities. But by the time you get it into the liquid state, the heat capacity has risen a little bit, so it takes a little more time to get a temperature change to happen there. And in the gas phase, it takes even a little bit more time, so it's a little bit higher on the heat capacity. And water does the same thing too. You can go back and check that out. Water has a low heat capacity in the ice form, a very high heat capacity in the liquid form, and a low heat capacity again in the steam form. So, and again, don't memorize those. If you ever need them, you could be probably given them. Now, there's another physical change that involves a heat change, and that is the heat of solution. When ions go into water, they get surrounded by water molecules, and the formation of these attractions releases heat. And so you might get some heat out of it. You might actually have to put a heat in because there are 3 separate energy changes needed to dissolve something. The sum of these changes is the heat of solution. You're likely going to be asked questions on this. For example, on the AP Chemistry Progress Check FRQs for Unit 6, there's a question about the attraction between the particles. So you have to kind of know this to answer that question. So it turns out if you want to separate the solute molecules, which you have to do to get them to break apart and dissolve into something, you have to put in energy. That requires energy to break them apart. You also have to make little spaces between the solvent molecules and separate those from each other, and that also takes energy to go in. So these first 2 are endothermic. Energy has to go in. But then when you take the solute and the solvent and give them new attractions to each other, energy is released back out. Is it the same amount of energy? Might be close, but probably not. And so we're going to take a look at this little graph. And whether your heat of solution is endothermic or exothermic depends on which set of interactions wins. If, for example, separating the solute and the solvent doesn't take much energy, but you get a bunch of energy out when the solute and the solvent get together, then your resulting energy change will be negative and you'll have an exothermic heat of solution. So you'll dissolve something, the temperature will go up, and heat will be released. On the other hand, if those solvent and solute particles require a ton of energy to break them apart from each other, and then you only get a little bit back when they make new attractions, then you have a net endothermic process, and you might put the stuff in your calorimeter cup, the temperature will go down at that point. Either way, though, you would calculate the heat of solution by using this relationship. It's going to be in kilojoules per mole, so you have to find the heat, and you have to find moles. So we find heat by doing negative Cm delta T for the solution that we made, and then dissolve it by the number of moles that we calculated. I did a whole video on how cold packs work and the heat of solution, and I did several of these example problems. So if you'd like to, go check out that video in the playlist. And now let's talk about enthalpy. And you probably heard this word, and it's kind of a weird word. one that we don't really use outside of chemistry class in a lot of situations. So, but enthalpy is a fancy term that we have because we always have fancy terms for things. For the heat, the energy, the internal energies of a system, how much energy is stored in a system. So when we look at a sample of matter, we can say there's energy in that matter, and that is its enthalpy. It's the stored energy. The problem with enthalpy is that it's really difficult to know exactly how much stored energy is in a piece of matter. There's a lot going on in there, and it's really difficult to quantify it, and it's a huge number anyway. What it is nice for is, though, is that it's pretty easy to calculate the enthalpy change or the delta H for a process. So, yes, there might be a certain amount of enthalpy in a substance. That enthalpy may go up or down to a new amount of enthalpy, but it's pretty easy to find the delta H, not the actual amount. So, enthalpy change, the change in enthalpy for a system is the same as the heat transfer in or out of a system. So, if we know how much heat goes in, how much heat goes out under constant pressure, under normal conditions, that is the enthalpy change for the reaction. So delta H is the enthalpy of the products minus the enthalpy of the reactants. That'll give us the correct sign of delta H. And in an endothermic process, delta H is positive. So the enthalpy is going up in the positive direction. In an exothermic reaction, the delta H is negative. Okay, and we'll revisit a couple of enthalpy diagrams. Delta H is negative if the system gives off heat to the surroundings, so exothermic. If the system absorbs heat from the surroundings, you'll see a positive or uphill energy diagram on that. And we can express this in a number of ways. One of the most common is by using a thermochemical equation, which are just like regular balanced chemical equations, but they also include a delta H at the end to show the enthalpy change for the reaction. And it's important to note, for example, carbon plus oxygen makes CO2. That delta H is minus 393. Whereas the delta H for this decomposition reaction is plus 114. The enthalpy change is per the number of moles in the coefficients. For example, in the second equation, 114 kilojoules are produced or absorbed for every 2 moles of NO2. So you have to sort of interpret it that way. For example, for every 1 mole of carbon, I get minus 393 out. But for every 2 moles of NO2, I have to put in plus 114. So make sure you note that proportion or that ratio. I have a couple more that I like to show in my class. One is the oxidation of iron to make rust, which actually happens in hand warmers, by the way. And that gives off 825 kilojoules of heat, which is plenty over the course of a few hours to keep my hands warm or my toes warm. And this one is a famous endothermic reaction. And I just recently saw a question about it, freezing the beaker to the board using barium hydroxide and ammonium thiocyanate. That actually takes in 287 kilojoules for every mole of barium hydroxide that's produced. All right, so then we get to questions like this, which you're likely to see. Going to one of my favorite reactions, this is the Thermite reaction. I have videos on that if you want to go check them out. Just search Thermite in the search bar and you'll see me doing some really fun things outside. Aluminum plus iron oxide makes aluminum oxide and some molten iron out of it, and 850 kilojoules are produced. But we might be asked this question: what if I have 50 grams of aluminum? Maybe I don't have 2 moles, maybe I have 50 grams. What amount of heat will actually be produced? And when you do this, and you know the delta H, and also an amount, convert to moles if necessary. You can follow these 2 steps, and then multiply by your delta H. So it goes something like this. I need to have it in moles, so 50 grams of aluminum. We'll do a quick 1 mole of aluminum, and I'm just going to round it to 27 grams of aluminum off the periodic table. And then I can take that negative 850 kilojoules, right there, and that is 850 kilojoules for every 2 moles of aluminum. So I have to put 2 moles aluminum on the bottom. Show you where that came from. And if I do that properly, then I get a negative 787 kilojoules out of it. So convert to moles and multiply by delta H if you happen to know what the delta H is. All right, we're going to get to our first pause the video moment. And I have a similar example. This is the combustion of ethanol. to make carbon dioxide and water, and the delta H is right there. Take a moment and pause the video since we know the delta H and we know an amount. See if you can calculate the amount of heat absorbed or released from this thing. I'll see you back here in a couple seconds. And if you were able to get negative 743 kilojoules out of it, then congratulations, you've mastered the convert to moles and multiply by delta H types of problems, which are fairly common and you're likely to see them. Section 7 is all about bond energies. And specifically, that bond energies can be used to calculate delta H for a reaction. Again, I just recently assigned the FRQ progress check from AP Classroom, and this type of question was on it. So let's review. We did this before. Bond energies, the formation of chemical bonds releases energy. As those atoms get closer and closer to each other and they start overlapping and forming that attraction, they move to a lower stress, lower energy situation, which happens at a certain distance from the nucleus. So there's a definite bond length for each different type of bond. And there's a definite bond energy that's released, and that's going to be like a negative value from the 0 point up here. So bond energies exist for all those chemical bonds. And you might find or have a table, something like this. This is a more exhaustive one. If you ever get to one of these questions in an AP exam FRQ, they're probably just going to give you a little one with just the bonds that you might need. Probably a couple of distractor bonds in there as well. But for example, a carbon-hydrogen bond, 413 kilojoules per mole. That's the unit. Carbon-carbon is a little less. Carbon-nitrogen is a little bit less, and so on. It's important to note that all of these up here are single bonds, but then you get down in here to double and triple bonds, and the energy goes way up because the formation of another chemical bond on top of the first one releases more energy, and by the time you get to triple bonds, you're just releasing a ton of energy. So know that those are there, and when you're doing bond energies, make sure you know which ones you're supposed to use. You might have to draw the Lewis structure to find out, am I working with a single bond or a double bond or a triple bond? Because that would affect your answer depending on what you're doing. And the way you use these to find delta H is by adding up the bond energies for the reactants, getting a total, and then subtracting the bond energies for the products. All right, it might make sense that if we're going to do a reaction, we have to first break apart the molecules that are already together, break apart those bonds. So energy has to go in, and we have to go up the energy ladder. Then when they get to past the transition state, and this is kind of what the transition state would be in a kinetics graph, like we did last unit in Unit 5, we have to get energy in, go up over the hump to that excited state or the activated state. Then the new bonds start to form and energy is released back out. And so if we add up the amount going in and the amount coming back out and subtract them, we will get a total. So I'm going to use an example that I used in class for the burning of methane. Okay. And when you might expect this to be exothermic, this actually runs our Bunsen burners. And I will say I should probably balance that. So CH4 plus two O2s makes CO2 and two waters. Now, if I were to find delta H for this reaction, I would have to add up the 4 bond energies that are here, 4 CH bonds for a total of 1652, and 2 O2 bonds. Now notice that this number here is actually the bond energy for an oxygen-oxygen double bond. It's not an oxygen-oxygen single bond. It's double bond because oxygen, when it is diatomic like that, actually is double bonded to itself. So again, if you didn't know that, you could draw the Lewis structure to find out it's double and then use the double. So I add them all up and I get 2648 in, and now you can imagine they're all separate atoms floating around, hanging out, introducing themselves to each other, getting ready to do the reaction, and then the reaction starts. And we produce 2 carbon-oxygen double bonds and 4 oxygen-hydrogen single bonds. And if you add all of those up, make sure it's a double bond, and you get a total of negative 3466. Adding up this minus this gives me negative 818. And so if you just remember, bonds broken minus bonds formed gives you delta H. You'll be able to handle that kind of question. A common theme for this chapter is how do we find delta H? How can we find delta H for a process or a reaction? And a second way, we just learned about bond energies, a second way to find the delta H for a reaction is by using something called standard enthalpies of formation. And the enthalpy change that occurs when 1 mole of a compound is formed from its original elements in their standard states is the standard enthalpy of formation. And so I'm just going to use a quick example. Let's say I wanted to whip up a batch of lead oxide, lead 2 oxide. I'm going to need some lead and a half of an O2 molecule, and I'll make some lead oxide. And when that happens, there's an energy change because we're forming chemical bonds. And that lead oxide, this reaction will have a delta H of negative 217.9 kilojoules. Okay. And that's basically saying, okay, I'll make my energy diagram. PB plus 1 half O2. We're going to go down in the energy ladder, negative 217.9 kilojoules. And we're going to get PbO down there. So this is what is essentially the enthalpy that exists inside 1 mole of lead oxide. Okay, we formed it from its elements and we got that energy change in it. Now, I talk about this with my classes also about how this is a negative value. And if we're trying to represent the energy in a sample, a mole of a sample, how can it be a negative value? Well, it's negative because it's down lower than where we started. And whenever you do a measurement of something or have a scale, you need a 0 point. And so scientists a long time ago decided that the enthalpy of elements by themselves in their standard states is going to be 0. Are they actually 0? No, there's a ton of energy inside all the elements. But we're going to call it 0 because it's easy for us to measure the enthalpy change when you start making compounds with those elements. And so you may have seen a table something like this. There's whole books you can buy with these tables in it. The internet is full of these tables where you can just look up different compounds and they have their delta HFs or heats of formation. These are saying they have enthalpy that is different than the elements they came from. Most of them are negative because we're forming chemical bonds and that releases energy, although some of them are positive. I'm thinking of some of these nitrogen containing ones way over here that have a positive delta H. But these are not numbers that you'd have to memorize. They would be given to you in any kind of table. You just have to know what to do with them. And what we can do then is by doing a form of Hess's law of heat summation, and that's what these summation symbols are for. And what we need to do is say, all right, if I want delta H for a reaction that contains molecules and compounds, add up the heats of formation of the products minus the heats of formation of the reactants. So you got to go right side minus left side, or products minus reactants. Let's see how that works. Example number 1, calculate delta H for the following reaction. Okay, so calcium carbonate decomposing into calcium oxide and carbon dioxide. Here's a mini table with some data in it that we need. And we can then say, if I want to do the delta H for this reaction, I simply have to add up, and I like to use these brackets to do it. Add up the two products. Calcium oxide is negative 635.1. Carbon dioxide is negative 393.5 minus the reactants. Now, sometimes you're going to have to do minus a negative, so you got to keep track of that negative sign, and it happens a lot. So minus 1207, and if I do that, adding up these minus this, I get positive 179. So I find out that it's endothermic. All right, and then we'll look at another example. I'm kind of doing these quick to save some time. You can always pause the video and try them if you want. Calculating delta H for this one. F2 plus 2 HCl's makes 2 HFs and a chlorine molecule. And they give us some standard enthalpies of formation. But on this one, there's a couple of distractor ones, so don't use those because they're not appearing up there, but they're there. And we want to add up the products minus the reactants. But you're probably sitting there thinking, wait a minute, Mr. Rudolph, there is no fluorine and chlorine down here. Like, it's not in the table. How am I supposed to know that? I'm sitting at the AP exam and I don't know that. Well, it turns out if we know that those are elements and that elements have enthalpies of 0, we can just simply put in zeros for those. So 2 HFs plus 0 for the chlorine minus 0 for the fluorine plus 2 HCl's, and I get a negative 362 kilojoules out of that. So again, products minus reactants if you're armed with the appropriate table. And I'm going to do one here that is kind of a fun one. I like to be inspired by real substances, real events, real samples. And I was inspired by a can of Coca-Cola that I happen to have out on my desk. I don't drink sodas that often, but it's fun to have once in a while. And I read on the back of the Coca-Cola that there's 39 grams of sugar in a 12-ounce can of Coca-Cola. And I thought to myself, if I drink that, and that sugar is glucose and some fructose, same chemical formula, and I metabolize it by breathing in oxygen and breathing out CO2 and H2O, how much energy am I going to get from that can of Coca-Cola? Well, it turns out I'm going to show you a couple of steps to this. First, I want to know delta H for this whole reaction. So I went to the chart. I added up 6 CO2s and 6 waters and got a total, minus the heat of formation of glucose, which is 1273, very similar to fructose. There's a mixture in there, and then 6 oxygens at 0 apiece, and I got a total delta H of negative 2803, and that's in kilojoules per 1 mole of glucose, according to that reaction. So that's great, 2800 kilojoules per mole of glucose if I eat them or drink it. Then I said to myself, well, that can in particular has 39 grams of glucose in it. And glucose is 180 grams per mole. And if I apply my, apologies, I miswrote 2803 kilojoules from the original reaction to that, this is a small amount of moles, so I get negative 607 kilojoules out of it. Again, convert to moles, multiply by the delta H. And that's that. And I thought to myself, well, I wonder how that compares. I want to know, because I live here in America, and for whatever reason, we're still doing calories most of the time. So I quickly converted that into food calories, which turns out to be 145 food calories. And interestingly enough, if you look at the label for a can of Coke, the calories that it lists is right around 140 calories. So this is a kind of a fun example to show that chemistry actually does work and that you do get results that you might expect using things like Hess's law of heat summation and converting to moles and all of that sort of stuff. So here's a picture of the label. So hope you enjoyed that. Fun fact, a cup of black coffee has about 5 calories in it. So I haven't added any sugar to this thing, so 5 calories down the hatch. I usually start doing Hess's law by doing this last section first before I do 6.8. I just like the way it flows better. But let's do it, and we will get this last section out of the way. 6.9 is all about Hess's law of heat summation again, but in a different form. Again, how can I find delta H for things? If a reaction can be considered the sum of 2 or more other reactions, then delta H for the reaction you want is equal to the sum of the delta H's for the other reactions. So it's a way of saying that if you start in one place and end in another place, it doesn't matter how you get there, the energy change will be the same. I always like to think about, traveling up maybe a mountain, like from the bottom of the mountain up to the top of the mountain. It doesn't matter which path I get there. If I start at the same spot and end at the top, my elevation change will be the same. And elevation is kind of analogous to energy in this situation. Let's see how it works. You might see a couple of equations next to each other or above each other, and asked to find delta H for a third or target reaction that you're wondering about. Let's take a look. Carbon plus 1/2 O2. If I take carbon and make carbon monoxide, I get 110 kilojoules out. I don't have to know that ahead of time. They just gave it to me. And then if I take that same carbon monoxide and add another oxygen to make carbon dioxide, in the second step, that's 283, the total is negative 393.5. If I add both of them up. If I do it all in one step, carbon plus oxygen makes CO2, I'll get it all at once. But if I do it in 2 steps, I get 2 smaller chunks of energy, but the total is the same. And that's the key, that the total can be added up to make a total. So here's another example. Methane reacting with oxygen makes CO2 and water, 802 kilojoules. But if I take that gaseous water and make it liquid water, right, I'm going to get more energy out, 88 kilojoules, as that condenses. So what if I want to know this reaction but with the water in the liquid state? The gaseous state water is going to cancel out, and I can simply add up these to get negative 890 kilojoules as my total. Okay? And we have a little enthalpy diagram. Notice the enthalpy diagrams do look different. There's no one enthalpy diagram that rules them all. You might see them in different patterns or forms. All right, let's take a look at this one. What if I decide I want to make some money and I want to take some graphite and make it into diamonds? That'd be really cool if I could do that. And I know that burning graphite gives me 393, burning diamonds gives me 395. Can I use this to find delta H for the target equation? Should I be putting in energy? Should I be taking back energy out? Well, we can do this, but there's a catch. And this catch is that the diamond is supposed to be here on the right, but up here it's on the left. Does that work? No. We have a couple of rules that we can manipulate the equations, but we have to manipulate them so that they do add up to the total. If the equation needs to be reversed, like I'm going to reverse this equation, the sign of delta H changes, but the value remains the same. If the equation is multiplied, maybe I have to double it to get 2 diamonds or something like that. The value of delta H is multiplied by that amount. The sum of the step equations must add up to the original equation. So if I go back to this one and say, you know what, I'm just going to reverse this guy and make it CO2 makes carbon in diamond form plus O2, then what happens is I'll cross this out. The CO2 is going to cancel. The oxygen is going to cancel both on either side, and I'll be left with graphite making diamond, right? And that's going to be an input of 1.9 kilojoules of energy. So I get these two to add up by reversing one of them. Let's do another example or two. This is another example. Let's suppose I wanted to whip up a batch of acetylene, C2H2. That's what we got. And I look up some reference equations. I know that burning carbon to make CO2 is negative 393. That's pretty common. Making water is negative 286. Burning acetylene is really fun because it burns and releases a ton of energy. So C2H2, making carbon dioxide and water, that's 1,300 kilojoules out. Do these add up to this one? And if they do, can I add up the total? Well, you might be looking at it and saying they don't add up because this is on the wrong side. And also I need 2 carbons and I only have 1 carbon. So take a moment and see if you can kind of guess how you might manipulate this series of equations to get the total. Back here in a couple seconds. Okay. All right. So the first thing I did when I did this is I reversed that first equation. I rewrote it in red so that you can see it. And that changed the sign of the delta H. So I'm going to use this red one. I'm going to ignore this black one now. I just reversed it. Now the C2H2 is on the appropriate side where it needs to be. Then the next thing I need to do is take care of this carbon because I need 2 carbons in it. So I doubled the second equation. You can do that. You just simply double the delta H at the end. So now I've got C2H2 on the appropriate side, 2 carbons on the appropriate side, a hydrogen on the appropriate side, and everything else is going to cancel. 2 CO2s, a water, the 5 halves O2 here and the 5 halves O2 here. And when I do that, I get positive 227 kilojoules as my answer on that one. So you're likely to see a Hess's law problem like this on the AP exam. And I would like to say that this also applies to delta S and delta G. Now, we haven't gotten to those yet. They're going to be in Unit 9, but delta S is the entropy change, and delta G is the Gibbs free energy change. Hess's law applies to all 3. So once you learn it once, you can apply it across the board. Take a moment real quick and see if you can get this one. Try to find delta H for the top reaction using those 2. Be back in here in a couple of seconds. And if you were able to get a positive 68 kilojoules on that, congratulations. We need to reverse this second one and then everything cancels. And one last pause the video moment using some enthalpies of formation. These elements making these compounds Those are enthalpies of formation right off the chart. But in this form, we could still do the thing where we can reverse and multiply. Take a moment and see if you can get the correct answer on this one to finish it off. And if you got negative 802 kilojoules by doing that, which matches the previous example from this video, then congratulations, you're mastering Hess's law. And that brings us to the end of AP Chemistry Unit 6. We'll finish off with the list of the topics again. If you have questions, you can send them to me in the comments or directly. You can also check out my playlist on YouTube to see more information, more in-depth information about a lot of these. And in the meantime, happy studying and have a great day.